And with this, we should be finishing this chapter. Remember the problem we did with the 2 stars. We did 2 times 10 to the 30th, and we did 6 times 10 to the 30th kilogram. And the distance between them was 40 times 10 to the 8 meters. And we also found that the center of mass was here, 30 times 10 to the 8 meters away from this guy. So this is the heavier one, the center of mass is closer to that. And we did several types of different questions with that. So now let's do this. What if these 2 systems go around each other? And so they go around each other, and they're going to go around the center of mass. So every time they go around, their center of mass should stay constant. So when this guy comes down here, let's say it comes like here, let's say here was the center of mass, this guy should have moved over here. Let's draw this a little smaller. So this guy moved this way, this guy moved from here to here. So this is a binary star system that revolve around their common center of mass. And then when this guy comes here, let's say, this guy is going to go over here. And then when this guy comes here, this guy is going to go over here. So this guy's going to do less of the motion. And then the lighter star, which we had called star 1, will do bigger motion. So what would be the period of that motion? How would you do something like that? So remember when I first developed the period equation, I was assuming that the distance is equal to the distance between the stars is also equal to the distance of the radius of the circle. Here it's a little different. So if I want to calculate the period of star 1, this was star 1, this is star 2, so we could say the force on 1 is equal to Gm1 m2 over the distance squared. That's equal to the mass of star 1. Let's do the period equation. 4 pi squared, mass of star 1, right, times the distance between times the radius over the period. So the radius, let's call that one r. 4 pi squared m1 r. So the difference now is that this distance between them is not necessarily the same as the radius of the circle that the star 1 is making. You see? So before we were saying this is d, we were getting d cubed. So now, and then this is t squared, right? T squared. So if we wanted to calculate the period of star 1, so we have m1, m1 going to cancel. We have the period of star 1 squared is equal to 4 pi squared over g mass of star 2, the distance squared, the radius, we can call this radius, the radius of the orbit of star 1. Okay, so let's calculate the period of star 1. 4 pi squared over 6.673 times 10 to the negative 11. Mass of star 2 was 6 times 10 to the 30th. The distance between them was 40 times 10 to the 8th. We square that. And the radius of the orbit of star 1 is what? That's the 30, right? Because if star 2 starts out here, star 1 starts out here, the center of mass is 30. So the distance here is just 30. So the radius of the star 1's orbit is 30 times 10 to the 8. So let's put all this stuff in. This is 4 pi squared times 40 squared this is going to be 10 to the what power? 10 to the 16, 10 to the 8, 10 to the 24th. Times 10 to the power 24. Divided by 6.673. Divided by, and then this is the mass of the star 2, 6. And then this is going to be what? 10 to the 19th. So divided by 10 to the power 19. And then we square root that. We get 68,796 seconds. Square root that. Now we divide that by 3,600 seconds. We can express it in hours. So T1 is going to be 19.11 hours. See? So that's the period. That's a pretty fast period. That's a binary star that's going around each other every 19 hours. That's most likely an over-contact binary. They're very, very close. Okay. Now, how about the period of star 2? So we have the force on star 2 is G M1 M2 over the distance squared is equal to 4 pi squared times the radius of star 2 over the period of star 2 squared. And then times we need the mass of star 2 times the radius of star 2. Mass of star 2 cancels, mass of star 2 cancels. We have the period of star 2 squared equals 4 pi squared over G, mass of star 1, distance squared, radius of star 2, mass of star 1 is going to be 2 times 10 to the 30th. And then here you have the distance between them, that's the same. So that's going to be 40 times 10 to the 8 squared. And then the radius is going to be, the radius of star 1's orbit is going to be what? Well, if this one was 40, right, from here to here was 40 times 10 to the 8. And then here to here was 30 times 10 to the 8. So the radius of star 2's orbit is going to be 10 times 10 to the 8. So 4 times pi squared times 1600 times 10 times 10 to the power 24 divided by 6.673 divided by 2 divided by 10 to the power 19. Okay? Square root that. Okay? Divided by 3,600. Lo and behold. Okay? What did I get? 19.11 hours. It should be the same, right? So they can't have different periods. By the time that this comes here, this should come there. By the time this comes here, this should come there. By the time this one comes to the other side, this one should come here. And by the time that they make a full circle, they both should make a full circle. So their period is the same. So if you can show that your answers are the same period, then you have done it correctly. Now the other way we could have done this is instead of recalculating it, I could have done a simple ratio kind of thing. I could have said instead of 30, this is 10. Instead of 6, this is 2. I could have done a simple ratio and it would have been quicker, but I just wanted to go through the whole calculation and show it to you from scratch. Okay, with that we end with our whole gravity section discussing satellite motion, everything, potential energy, kinetic energy. Next time we'll do fluid statics, fluid dynamics. We'll talk about Pascal's law, Archimedes' principle. We'll talk about Bernoulli's equation. Okay, bye.